Hello everybody. In this video we are going to start looking at the electromagnetic spectrum. We only have a couple more videos after this one, so we are getting close to the end. Just a quick note before we get into the video. If you are cross-referencing this video with the PowerPoint that is on the website, you might notice that the PowerPoint on the website has a few slides that are missing in the video. Just in the interest of time, I'm not going to be covering a few things like illuminance and luminous flux. So you might see them if you look at the PowerPoint on the website, but you won't be doing any homework problems about that. You won't see any problems about illuminance or luminous flux on the test, so we don't really need to worry about those. This PowerPoint is going to be a little bit different. The majority of this PowerPoint is going to be on background information, and the math won't be until the last few slides. So that is going to be a little different than how these PowerPoints usually work. The vast majority of this PowerPoint is going to be about more of a narrative than looking at the math of how light works. But you might still see a question or two about this stuff as a multiple choice question on the last test. So pay attention. All right. First thing I want to do is just talk about a little very brief history of our understanding of what light is. Right. If we go back to about 1000 AD, the philosophers and the scientific thinkers of the day proposed that light was made up of these tiny little particles. They had no idea what these particles were. They had no idea how they behaved. They really knew nothing about them, but they thought that light was made out of particles. And they called these particles corpuscles. We now call them photons, but back then they called them corpuscles. If we fast forward to the age of Isaac Newton, you know our buddy Newton, I mean, heck, the dude invented calculus. What more do you need to say? We've talked about his laws of motion. We've talked about his laws of gravitation. We're going to talk a lot about him when we talk about optics coming up in a week or two. So he was a busy guy. He was just a busy guy. And Newton agreed with the idea that light was made out of particles. And he used this idea, this model of what we call the particle theory of light, to explain how light reflects off of surfaces and refracts through different mediums. So how light would, say, reflect off of a mirror or refract through a lens. And the math worked out, and it did a good job of explaining how light behaved in those terms. And he used the particle theory. Around the same time as Isaac Newton, there was another scientist, Christian Huygens. He was a rival of Newton. The guys didn't like each other very much. They used to badmouth each other all the time. They used to talk about each other behind their backs. It was pretty ugly. But Huygens thought that light behaved more like a wave than a particle, and he proposed that light was a wave and it wasn't made out of particles. And the two went back and forth, and scientists were either in Isaac Newton's camp and agreed with the particle theory of light, or other scientists agreed with Huygens and thought that light was a wave and agreed with his wave theory. There were like two camps, and these two camps, again, didn't like each other very much. They really didn't agree on anything, and they couldn't come to kind of consensus about what light was. Okay, so we have two camps when it comes to what light is. We had the particle theory of light, which is what Newton was proposing, and we had the wave theory of light, which is what Huygens was proposing. There were a number of experiments that went on through the decades and the centuries even after Newton and Huygens made their theories of the particle theory and the wave theory. And some experiments supported Newton's particle theory, some experiments supported Huygens' wave theory. And let's take a look at a couple of those. The first one, again, I'm not going to get too deep into this. In class, I usually explain this in a little bit more detail, but just give you guys a quick overview. In about 1801, there was a scientist named Thomas Young, and he did this famous experiment. It's called the double slit experiment. Again, I'm not going to get into what the experiment was or how he conducted the experiment. But basically what the experiment showed was that light undergoes interference, constructive and destructive interference. Just like if you have two pebbles and you throw them into a pond and you look at the ripples coming off of each of the pebbles, those waves will interfere with each other. Light does the same thing, which supports the wave theory of light. Then came another scientist, James Clerk Maxwell, in 1865, and he showed that all electromagnetic waves travel at the speed of light, which means that they are all related to each other. And when we talk about electromagnetic waves, we'll look at the spectrum in a little bit. We're talking radio waves, microwaves, visible light, gamma rays, a whole array of rays. So we have different experiments now. Some of them are agreeing with Newton's particle theory, and some of them are agreeing with Huygens wave theory. Let's fast forward to the early 20th century. A German scientist named Max Planck did some experiments to show that electromagnetic radiation is quantized. Now remember, the word quantized means that it comes in discrete packets, just like electric charge is quantized. You have one proton with a... So now we have light, and we have experiments that show that sometimes it behaves like a wave, sometimes it behaves like a particle. And when we have these particles of light, we call these particles photons. So a photon is one particle of light. And we know that each photon, or all photons, have a certain amount of energy, and different colors of light or different wavelengths of light, not just light actually, again we're talking about the entire electromagnetic spectrum, but they each have different frequencies and different amounts of energy. And so we know that the energy associated with a photon is equal to h, which is something called the Planck constant, times the frequency of the light, or the electromagnetic wave, I should say. We know that this h here, the Planck constant, is equal to 6.63 times 10 to the minus 34th joules times a second. Now, I will tell you right now that I'm never going to ask you about this on the test. You don't need to memorize it. If you look at the formula sheet for the test that I have posted up in the toolbox, it's not there because you're not going to need it. I'm just showing it to you just so you have an idea of just what kind of numbers that we're dealing with. But the important thing to note here is that this equation kind of encompasses both the particle theory of light and the wave theory of light. Each photon has a certain amount of energy which supports the particle theory. Because it behaves like a particle, it has a certain amount of energy. But it also has a particular frequency, just like a wave. So this equation helps to kind of combine the particle theory of light and the wave theory of light. So now that we know light has a dual nature, it can behave like a particle or it can behave like a wave. We can design experiments that test the particle nature of light, and we can design experiments that test the wave nature of light. What we can't do are design experiments that test both the wave and particle nature of light at the same time. If we design an experiment to test the wave nature of light, it's going to behave like a wave and not like a particle. If we design an experiment to test the particle nature of light, it's going to behave like a particle and not like a wave. So we can't test both of those things at the same time, but we can test them independently, and we've done many experiments that do just that. So now we have different forms of electromagnetic radiation, and we'll talk about those in a minute, but things like visible light, radio waves, gamma rays, X-rays, ultraviolet rays, they're all distinguished by their frequencies and their wavelengths. And our equation for that is going to be, and this is just a simple equation, but the equation for that is going to be C. We'll talk about what C is in just a second. C is going to equal the frequency times the wavelength. And C is a special value, and that is the speed of light in a vacuum. And that speed of light in a vacuum is 3.00 times 10 to the 8th meters per second. That's what we call the speed of light. Right, and this is just another form of the equation. The wave speed equals frequency times wavelength, but the speed that we're talking about now is the speed of light, so we use the symbol C to denote that. And that's a symbol that we're going to be using a lot for the rest of the time that we have together. It's kind of like how G is 9.8 meters per second squared. C is 3.00 times 10 to the 8th meters per second. One note about the speed of light is what we call our universal speed limit. Nothing in the universe can travel faster than light, and that's been proven that was proposed by Einstein. It's been proven experimentally time and time again. Matter of fact, that's one of the more thoroughly tested theories ever proposed by anybody. And every time somebody does an experiment to test that, it agrees with what Einstein said about nothing being able to travel faster than the speed of light. And we'll talk about what different forms of the electromagnetic spectrum in a minute. But when we talk about visible light, the light that the human eye can detect, that range, or that portion of the electromagnetic spectrum, ranges from about 400 nanometers to about 700 nanometers. And one thing about the divisions between the different portions of the electromagnetic spectrum, there's no sharp division, no real clear dividing line between one type of electromagnetic wave and another. All right, and that brings me to a story that I want to tell you guys. So it is now story time with Mr. Tiesler. As you guys know, I used to do theater lighting professionally before I became a teacher. And I think I talked about the job that I used to have for a company called Roscoe, where we we manufactured equipment that theaters use for lighting. It was used a lot in themed entertainment, so theme parks, things like that. We used to make they still do. They make the gels, the colored gels that we put in front of lights to make them different colors. And part of my job was I used to have to go down and consult for the theme park when they were trying to do something new for some of their rides. I think I've told you some of these stories before. Well, one time I had to go down to Universal Studios in Florida. I don't know how many of you guys have been down there. It's a fun place. And they used to have a ride. I think they may have gotten rid of it. I think they got rid of it a bunch of years ago, but maybe when you were younger, you went on it. They had a ride based on the Back to the Future movie. And the ride was basically a motion simulation ride. So you had these cars, the DeLoreans that are in the movie, and you sat in the car, and you were surrounded by this huge screen that moved around, and the motion simulation vehicle bounced around and everything like that. And the way the ride was designed, there were about 5 cars in a row, and then there were about 3 different levels of cars. So there were about 15 different cars that were occupied at the same time, and this huge screen kind of wrapped around where the cars were. And when the ride started, when they started the simulation, they would take these cars and they would kind of extend them over the edge so that you would feel like you were a little bit more surrounded. But that also meant that if anybody tried to get out of the car while the ride was in motion, that they could fall quite a ways and get hurt. So what people didn't know was, when you were on that ride, on each one of those cars, there was a camera with an infrared light attached to it, focused on each one of those cars. And that camera only detected infrared wavelengths of light. So they had an infrared lighting fixture that was trained on the cars. You couldn't detect it with your eyes, but the camera could. And behind this big projection screen, there was a desk there with all these different monitors, and there was a person whose job it was to sit there and watch everybody go on the ride. So people had no idea they were being recorded and watched while they were on the ride. And they used to do some very interesting things while they were on the ride, I am told, but they had no idea that they were being filmed. I don't think they recorded it. I think they may have recorded it for security purposes, but I don't think they ever kept it. But the reason why I knew that is because after a while, the filters that only allowed the infrared frequency of light to shine through started to fade after like 10-15 years. So they need new filters on the ride. So I had to go and design new filters that would only allow certain frequencies of light to go through there. So I had to go down there and consult with them and do all sorts of things and go behind the scenes on the ride, which was kind of cool. But I found it was very interesting that people were being recorded on the ride and they had no idea about it. So if you ever went down to Universal when you were younger and you went on the Back of the Future ride, you were being watched, just so you know. All right, let's take a look at the different parts of our electromagnetic spectrum. You may have taken a look at this in the earlier grades. I'm not going to go too crazy with this, but I just wanted to show you the different portions of the electromagnetic spectrum so you are familiar with it. Now, the different parts go from things that have very, very long wavelengths. If you notice here on the right-hand side, we have the wavelength of that part of the electromagnetic spectrum, and on the left side, we have the frequencies. Now, the frequencies increase as you go from the bottom to the top. We start with the frequencies of 10 to the third on the bottom, all the way up to 10 to the 22nd at the top. The wavelengths are in the opposite direction. They get longer as you go down the diagram. So they go in the opposite direction. So if we look at the portion of the electromagnetic spectrum that has the longest wavelength, that is the AM radio portion of the spectrum. I don't think anybody here listens to AM radio anymore. I don't think you guys even listen to radio these days. But that is in the kilometer range of wavelengths for the spectrum. Then from AM radio, we get into the TV and FM wavelengths for the electromagnetic spectrum. Right. After that, we go into microwaves. And that is in the centimeter range for the spectrum. Sorry, somebody just texted me. That's what that noise was. After microwaves, we get into the infrared portion of the electromagnetic spectrum, and that is called infrared because it is just below the red portion of our visible section of the electromagnetic spectrum. So this very, very narrow band right here is the visible portion of the spectrum. And if we could break that out, we have all the different colors of the spectrum. If you guys remember Roy G. Biv, we have the red, orange, yellow, green, blue, indigo, and violet portions of that. Above the visible light, we have the ultraviolet portion of the electromagnetic spectrum. Ultraviolet rays are what give us our suntans and sunburns in the summer. I got a little bit of sunburn when I was kayaking last weekend. Right. Again, it's called ultraviolet because it is above the violet portion of the visible range of the electromagnetic spectrum. Above ultraviolet, we have X-rays, and beyond that, we have gamma rays. And we distinguish all those by their frequency and their wavelength. We're going to talk a little bit about frequency, but we're really going to focus on wavelength for a lot of these. And just to give you guys a heads up with some of these metric prefixes, again, some things that you're going to need to be familiar with. Remember that that mu there is micrometers. And that is going to be 10 to the minus 6 meters. NM is nanometers, so be familiar with that. You're going to see that a lot when over the next couple of weeks. Nanometers is 10 to the minus 9th meters. And again, I will give you the metric conversion chart on the test. You'll see that it is on the formula sheet that I posted in the toolbox on the website. And PM is picometers, which is 10 to the minus 12th. So get familiar with those, especially nanometers, because again, you're going to be using them quite a bit. All right, next thing I want to do is just go over a very, very brief overview of each portion of the electromagnetic spectrum. Again, very, very brief. We're not going to get into a lot of detail at all. But if we start with the longest wavelength and the shortest frequency, we have our radio waves. Radio waves are used for communication. So again, radio, television, things like that. You know, a lot of communication systems will use a radio wave portion of the electromagnetic spectrum. Next up, we have microwaves. Microwaves are used for radar. They're also used for communications as well. A lot of our cell phone signals, when they need to be sent over long distances from towers to central locations, they use microwaves. They're very well suited for radar, so it's used in radar applications as well. And then again, we have our trusty microwave ovens. So those use microwaves to excite the water molecules in our food and heat our food up. Next up, we have infrared waves. Now, a lot of times people mistakenly refer to infrared radiation as heat. It's closely associated with thermal energy, but there's some differences there. Again, I'm not going to get too deep into this. I'm not going to get too crazy with it, but there are some differences there. Infrared waves are produced by any object that gives off heat, and we know that all objects do give off heat because they do have molecular energy. They are also readily or easily absorbed by most materials, so we absorb a lot of infrared electromagnetic radiation, and we also give it off at the same time. The visible spectrum, again, that's just the portion of the electromagnetic spectrum that is detected by the human eye. It goes between 400 and 700 nanometers. Right. It's the part that's most important to us because we are mostly visual creatures and we are pretty lost without our eyesight, so that part of the spectrum is really important to us. And our eyes are actually most sensitive at about 560 nanometers, which is somewhere between the yellow and green portion of the spectrum. Ultraviolet radiation covers from about 400 nanometers, which is where our violet end of the electromagnetic spectrum ends, to about 0.6 nanometers. Sun emits a lot of ultraviolet radiation. It shoots it out into space. A lot of it reaches the Earth. Most of that ultraviolet radiation, which by the way is really harmful to us, most of that ultraviolet radiation is absorbed by ozone in the stratosphere. And that helps protect us from this harmful radiation. Like I said before, ultraviolet radiation is responsible for giving us our suntans and sunburns, but it's also responsible for things like melanomas and skin cancers. So the more ultraviolet radiation that reaches the surface of the Earth, the more harmful it is to us. And if we didn't have ozone in the atmosphere that was absorbing most of that ultraviolet radiation, life wouldn't exist on this planet. We'd be like French fries under a heat lamp at Burger King. It wouldn't be pleasant, and we wouldn't last very long. So let's say hooray for ozone. Right, X-rays, really the only thing I can go into a lot of detail about X-rays. I'm not going to. Just to really know that X-rays, we use them as diagnostic tools for medicine. This is usually the point where I would show you guys an X-ray of my broken leg, but a lot of you guys have probably had X-rays for various reasons in your lifetime. Again, that's just another portion of our electromagnetic spectrum. The final portion of our electromagnetic spectrum are gamma rays. Now, gamma rays are the highest energy portion of the spectrum. They have more energy than other forms of electromagnetic radiation. And when they're absorbed by living tissue, by people or other living things, because they have so much energy, they do a lot of damage to our living cells and all the tissues that fall within our bodies. So a lot of radiation sickness that comes from nuclear accidents or nuclear weapons is caused by gamma rays. When they have to do all the protection at like nuclear power plants, for example, what they're protecting us from are these gamma rays that are being emitted by the radioactive material that is undergoing fission and creating all the heat that they're using to generate electricity. One other note on all these different parts of the electromagnetic spectrum, we can use them to find different parts of information about different objects or the same object. In astronomy, we use telescopes that look at different parts or different bands of the electromagnetic spectrum, and they can tell us different bits of information about distant objects in the galaxy, such as other stars, other galaxies, quasars, pulsars, things like that. So we have telescopes that use visible light, like a typical telescope that you would think of, but we also have radio telescopes that look at radio waves. We have X-ray telescopes, and we have microwave telescopes, and they sometimes all train all those different telescopes on the same object, and those different telescopes will give us different bits of information about that same object. So I think that's kind of cool. All right, let's talk about sources of light. Now, we say that light comes from sources in the form of a ray. An array is just an approximation so we can show photons of light in the direction that they travel. Now, an object that emits its own light is what we call a luminous source of light. A light bulb, the light bulb that is in my ceiling, that is shining down on me, is a luminous source. It's emitting its own light. A star like the sun is a luminous source. It emits its own light. An illuminated source of light is an object that reflects light. The reason why you can see my face right now is because the light is shining from the light bulb in my ceiling, coming down, bouncing off of my skin, and then going into the camera on my laptop. So the light is reflecting off of my skin, and that's why you can see me. And by the way, none of you guys can see me right now, just so you know. No, I haven't completely lost my mind again. But the reason why you can't see me is because all you can see is the light being reflected off of me. Our eyes are designed to see reflected light, and that is their only job. So as the light is reflected off of my skin, off of my shirt, off of the wall behind me, it's going into the camera, which is then going into your eyeballs. And your eyes see all of that reflected light. So that's what your eyes do. So none of you guys can see me. You can't even see your computer. All you can see is the light that is being illuminated by your computer. Your computer screen is a luminous source of light. So y'all can't see me right now. I'm gone. I'm going to spend a couple of slides talking about different colors of light. When we have light that is coming from a luminous source like a light bulb, it looks like it's white light, but that white light contains all of the different colors that fall within the visible spectrum. So remember Roy G. Biv, all of those different colors, like the colors of the rainbow, are all formed within that light. We can break that down into 3 primary colors, and the primary colors of light are red, blue, and green. Now you might be saying, wait a minute, Mr. Tiesler, my art teacher always told me that the primary colors were red, yellow, and blue. And I'm not going to say your art teachers are wrong, but I am going to say that your art teachers weren't being specific. Red, yellow, and blue are the primary colors of pigment. Red, blue, and green are the primary colors of light. And because we're a physics class, we're going to ignore pigment and we're going to talk about light. So from this point forward, the primary colors are going to be red, blue, and green, not red, yellow, and blue. Now we can take different colors of light and we can mix them up. And again, this is kind of where my interest lies in theater lighting. I do this all of the time. But if we take 2 primary colors and we combine them, we are going to have what we call a secondary color. So if I mix red and blue, which are 2 of my primary colors of light, I am going to get purple or magenta. If I mix red and green, I am going to have yellow light. And if I mix blue and green, I am going to have cyan, which is bluish green. If white light contains all the different colors within the spectrum, if I take a primary color and the secondary color that's combined by the 2 other primaries and I combine them together, then I can create white light. So if I take blue and yellow, now remember yellow is the secondary color by the combination of red and green. So if I mix blue and yellow, which yellow is made out of red and green, that will give me white light. If I take red, which is a primary color, and combine it with cyan, which is the combination of blue and green, that will also give me white light. And if I mix green, which is one of my primary colors, with magenta, which is a secondary color formed by blue and red, that will also give me white light. This is just a color wheel that kind of describes what I spent the past couple of slides telling you. We have our 3 primary colors of light. We have red, green, and blue. Those are my 3 primary colors. If I combine green and blue, I will have cyan. So that's my combination of green and blue. If I combine yellow and red, if I combine red and green, which are my 2 primary colors, I will get yellow as my secondary color. And if I mix red and blue, I will have magenta. And if I take all 3 of my primary colors and I combine them, I will get white light in the center. All right, so that does it for our background information. Now let's start applying some good old-fashioned math to this stuff. And again, there's a bunch of stuff that we're not going to cover in this video just in the interest of time. So we're not going to get into luminous flux or luminance or any of those things. We're really going to just focus on the Doppler effect as it applies to electromagnetic waves. Now, we covered Doppler effect last week with sound. And there are a lot of similarities between the 2 because just like a sound wave, electromagnetic waves can undergo a Doppler effect as well. There are, however, a couple of important differences. Sound waves require some type of medium to travel through. In the case of what we were talking about last week, the sound waves were traveling through air. Electromagnetic waves do not require a medium to travel through. So we don't have to account for the speed of the electromagnetic waves. We're just going to assume that the speed of the electromagnetic wave is always going to be equal to the speed of light, which is our 3.00 times 10 to the 8th meters per second. So if you remember when we did the Doppler effect for sound waves, we had to worry about the speed of the sound wave, and that was our v without any subscript to it. We don't really have to worry about that here. And because light is always traveling at 3.00 times 10 to the 8th meters per second, as far as this is concerned at least, we don't really have to worry so much on the frame of reference. When we're looking at sound waves, we had to always worry about, okay, how is this one object moving in relation to the other, as opposed to some frame of reference, which is usually the Earth. So we had, say a car was driving down the highway at 65 miles per hour or 30 meters per second. Well, that 30 meters per second was relative to the Earth. We don't really have to worry about that type of frame of reference with electromagnetic waves either. Let's take a look at the Doppler equation for electromagnetic waves. There are some similarities to the Doppler equation that we used for sound, but there are also some differences. I know that the frequency of the observer is equal to the frequency emitted by the source times 1 plus or minus the relative velocity between the source and the observer. So the v is just the relative velocity between the source and the observer. And c is our speed of light of 3.00 times 10 to the 8th meters per second. Now we have this 1 here because, again, we don't have a medium that it is traveling through, so we don't have to worry about that. So that kind of takes the place of that first part of the parentheses in the sound Doppler equation. Now the next thing I want to talk about here is the plus and minus sign. We use a plus sign if the source and the observer are moving toward each other. And we use the negative sign when the source and the observer are moving away from each other. So that kind of matches the way we did it with sound as well. When we were looking at the frequencies with sound, if the object was moving toward the other, it was positive. If it was moving away, it was negative. We're doing the same thing here as well. Now we could also look at the Doppler shift for electromagnetic waves in terms of the wavelength. And when we look at the Doppler shift in terms of wavelength, we have a different formula. And that formula is the observed wavelength of light minus the wavelength emitted by the source is equal to the change in the wavelength. And that change in the wavelength is equal to plus or minus the relative velocity between the source and the observer divided by the speed of light times the wavelength emitted by the source. Now let's talk about the plus or minus sign for a moment. In the wavelength equation, we use positive if the source and the observer are moving away from each other, and we use the negative if they are moving toward each other. Now that's the opposite of direction that we used for frequency, but now we're working with wavelength, so it's reverse, and that can be kind of confusing, so please be careful about that. Remember, when we're dealing with the wavelength equation, we use the positive sign if the source and the observer are moving away from each other, and we use a negative sign if they are moving toward each other. One last note on this, and then I'm going to shut up. So you're welcome for that. You may have heard of the terms redshift and blue shift, and that's a term. Those are terms that are used in astronomy to refer to whether objects are moving away from the Earth or toward the Earth. And things are redshifted. Objects are redshifted when they are moving away from the Earth because the relative motion between the objects is away. The wavelengths are going to be shifted toward the red end of the spectrum. And they are blue shifted when objects are moving toward the Earth because the wavelengths are going to be shifted toward the blue end of the spectrum. So that's kind of a really cool thing, I think, in astronomy, that even though they're looking at like galaxies and other celestial objects that might be millions or even billions of light years away, they can tell how fast those objects are moving because they're emitting a light, and that we know that that light is being emitted at a certain wavelength. Because say if it's emitting hydrogen, if it's made out of hydrogen, we know what wavelength of light hydrogen emits. When we look at that wavelength here at Earth, we can see if it's shifted toward the red end or the blue end of the spectrum of what we know hydrogen is supposed to be. And from the amount that it's shifted, we can determine how fast that object is moving. So even though things might be at the other end of the universe, we can still tell how fast they're going, and we can tell if they're moving toward the Earth or away from the Earth. And I think that's kind of cool. All right, that does it for the electromagnetic spectrum. We're going to be working on this for a few days, and then we are going to move on to optics. So I'll see you when we talk about optics.